Hello and welcome to Physics Online. This is Teacher Patrick. I hope you have a wonderful lesson, and if you've got any questions, please leave the question in the post below. Okay, today we're going to look at Newton's Laws, Chapter 2. The objectives at the end of this week, you should be able to understand that mass is a property of a body that resists change in motion. We can also call that inertia, and we'll look at that. Recall the relationship F is equal to ma, the resultant force is equal to the mass times the acceleration, and solve problems using it. Appreciating that the acceleration and the resultant force are always in the same direction. And then state and apply each of Newton's laws of motion. Now the next part is a bit of word consciousness, just to know where the words come from and what they mean. So the first word, motion, comes from the Latin word movere, to move. The next one comes from the Latin word force, comes from the Latin word fortis, to mean strong. Then resist, Latin word, part of the word is sister, which means stop. Okay, accelerate, Latin word accelerat, which means to be hastened or hasten something. Resultant comes from the Latin word resultere, to result. Inertia comes from the two Latin words inerse or inert, which means inactive. And direction comes from the Latin directus, which comes from two parts. The die meaning distinctly, and the regere being to put straight. Sorry for my pronunciations if it's not correct. Okay, Newton's first law. So Newton's first law of motion states that an object will remain at rest or in a state of uniform motion unless it is acted upon by a resultant force. Okay, so the object will remain standing still or will remain moving at a constant speed in a constant direction unless an external force causes it to change. Now we can also look at it in terms of inertia. Inertia is a property of matter by which it continues in its existing state of either rest or uniform motion in a straight line unless that state is changed by external force. Okay, so inertia, you can see, is very closely related to Newton's first law. Inertia, like I've said before, is the personification of Newton's first law. Sometimes Newton's first law is also called the law of inertia. We can see that if you look at the highlighted words, that there is definitely a resemblance. Okay, so here's a few applications. First, why do we need to wear a seatbelt, especially if you're a giraffe? Now, the giraffe is moving at the same speed of the car. Its neck wants to continue moving, but when it hits the wall, a resultant force is applied to the car, but not to the giraffe's neck. Therefore, we can get whiplash or injured with car accidents. Very important to wear your safety belt. If the safety belt was not there, the whole body of the giraffe would have continued moving. Okay, the next one here, why you do not spit directly up in the air when moving in a vehicle, especially if you're a llama. Okay, now, if you are busy moving, okay, the spit inside of your mouth is moving at the same speed you are. If you spit up into the air, the spit will have the same movement that you will have, and therefore it will land on your head again. Now I know this is only if we exclude air resistance, but the principle still applies. If you jump off a moving car, you will hit the ground at the same speed as which the car was moving. Okay. The next one is what happens to a hamster when the hamster stops running. Okay, so the hamster, when it stops running, okay, wants to stand still on the place where it was. Okay, what we see here is that the external force, the friction between the feet of the wheel and the hamster, causes the hamster to continue in its state of motion that the wheel had. So the hamster does not stand still where it was. Okay, the next part here, we look at what happens when an elephant stops blowing on your pinwheel. So when the pinwheel stops, okay, the elephant exerts a resultant force, and while the resultant force is exerted, the pinwheel starts moving. The moment the elephant stops blowing the pinwheel, the pinwheel will, due to friction and other resultant force, slow down and stop again. Okay, the next example is an example where we can see that objects want to remain at rest. Okay, so you'll see this dinosaur here. The dinosaur, the moment the trampoline starts moving, the dinosaur stays in its positions until gravitational acceleration starts acting on it. So what you'll see there is it starts moving very slowly compared to the movement of the trampoline. Okay, just to see it again. Okay, that proves to us that the object wants to remain stationary. And there's an external force. In this case, the external force is gravity initially, and then once the trampoline comes up is the force of the trampoline. Okay. Next, we're going to look at Newton's second law. Newton's second law states that if a resultant force acts on a body, it will cause the body to accelerate in the direction of the resultant force. Now, up to there is the official definition. The next part explains the formula. The acceleration of the body will be directly proportional to the resultant force and inversely proportional to the mass of the object. Okay, so what does that mean? If we look at the following example, okay, first we'll look at the formulas. The formula is F res is m times a. Okay, if we rearrange the formula to make a the subject, the acceleration the subject, we see that the acceleration is directly proportional to the resultant force and the acceleration is inversely proportional to the mass. Now, if we look at the following example, we have one guy at the top pushing with a certain amount of force, and then we have two people with double the force. When I double the force, I will have double the acceleration. In the next picture, we have the same person with the same amount of force, but the one is pushing a lighter object and the one is pushing a heavier object. The mass is inversely proportional to the acceleration when the force stays the same. So the bigger the mass, the smaller the acceleration. Okay, here we see a weird looking foot kicking a bowling ball or a balloon. Okay, since the bowling ball is much heavier, it accelerates less. Since the balloon is much lighter, it accelerates more. Okay, Newton's third law states that when two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. Okay, we can also quote it differently and say if object A exerts a force on object B, then object B exerts a force of equal magnitude on A but in opposite direction. Now guys, the first one up is the Cambridge definition. The next one is one that will just help you to understand it. Very important to see, and you're going to look at the following. The effect of the force is not the same, but the forces are the same. So the result of those two forces might look different, and that's what you're going to see in the following videos. Firstly, here we see that these two people exert a force on each other. Okay, the forces were not equal. The forces were equal, but the effect of the force is not equal. She gets flung through the air and he remains standing still. It might have to do with his weight being different to hers. Hopefully she didn't get hurt too much. But you can clearly see here that although the forces are opposite but equal, the effect of those forces are not necessarily the same. And that's why I sometimes get confused with Newton's third law. Okay, the next example is of a person shooting a gun. Now, the bullet gets shot forward with a very, very big force. The gun will experience an opposite but equal force. Now, the result of the gun is not always seen as much as we see it here. This is because the person is holding the gun wrong. If you start shooting, if you held that close to your face, you would most probably bruise your face or break your cheekbone. If you held it close to your shoulder, you can even dislocate your shoulder. Therefore, there's specific techniques in shooting a rifle. So the bullet moves out with a certain force forward, but the gun experiences a certain force backwards. Okay, here a guy learns how to practice how to shoot a bazooka. Same principle applies. The projectile is shot forward with a tremendous force, but the opposite but equal force is exerted on the bazooka. Now, if you do not hold the bazooka still, the bazooka will shoot backwards, and that's what gave this guy such a big fright. Okay. Next one we can see here with a balloon. Normally when we release a balloon, it just blows out air and it starts flying in all directions. Okay, so what we see here is the balloon is exerting through the straw, pushing out the air. The air is pushing backwards, okay, or the balloon is pushing the air out backwards, but the air is pushing the balloon, in this case the balloon on the cart, forwards. Okay, so guys, that is the explanation of Newton's laws. I hope you have a good understanding now, and if you have any questions, you can ask me. Just the next challenge here. Here we see Newton's cradle. It's a, yeah, this is a familiar toy. Which law do you think does this represent? You can leave your answer as a comment below. I hope you have an awesome day, and thank you for participating. Goodbye.